Hi, good morning. I hope you're doing good. As you can see here, I'm sitting at the Apple Park, and yesterday Apple has announced all the iPhone 17 models, and I'm really excited about the models, but there's no improvement in Apple iPhones or something. No, I'm just kidding. I'm not sitting. This is my background. So I have some of the results over here, um, looking at the RNA expression data or the gene expression data. And I want to perform some machine learning algorithms on the RNA expression data, which is, I think, much more beneficial if you have millions of data, like the samples, like millions of samples, and then you have these log2 values where you have like a drug sensitivity, disease status, or IC50 of that particular drug, and then your log2 values. And you want to perform the machine learning algorithm on that. So if I want to apply the machine learning algorithm, for instance, think of it like a story, because I'm going to show you only a small data set where you can perform the machine learning algorithm. For instance, if you have 100 people and some are healthy and some with the disease, and you looked at 50 different genes in each person to see if you could tell who was sick just by looking at the genes. So 50 healthy people and 50 sick people. And looking at the 50 genes in each person, can we predict who's sick just from the genes? Yes, we can. We have to apply these five different algorithms. I'm taking simple algorithms like random forest, SVM, logistic regression, XGBoost, and neural networks. And when we apply these machine learning models on these particular genes or the data set, so the final report card that we see is based on some values. Some values like accuracy, the ROC-AUC, which is called the magic number, and then you have the precision, the recall, the F1 score, etc. Okay, and we need to understand not only the data, but also the results that we are getting from all these machine learning models. So accuracy is defined like out of 100 guess, you have these 50 healthy and 50 sick people, and out of these 100 guess, how many did they get right? How many are actually sick? So if it says that 80% accuracy, that means 80 out of 100 is correct. That's accuracy. And if you have this ROC-AUC, you might often encounter these values in any sort of machine learning tutorial or any sort of pipelines. So this is called the magic number, or this is the most important number. So imagine if you have a magic scale from 0 to 1, we consider it simple. So 0 0.5 means as good as flipping a coin. So you never know whether you are getting the head or you might get tail. So 0 0.5 is that value. 0 0.7 is pretty good detective. 0 0.8, great detective. 0 0.9, almost perfect. And 1.0 is perfect. Never happens in real life though, especially in case of RNA sequencing data or any sort of clinical samples. It's never going to happen. So if you are getting one, then you might consider looking at your data. The next thing is the precision. Precision is something like when they are sick, how often they right. If the detective points at 10 people says you are sick, precision tells how many of those 10 actually are sick. Okay. The recall values, how many sick people did they actually find? If there are 10 sick people in the room, recall tells us how many of those 10 the detective actually found. And the F1 score is like a balance score. So this is like getting both the precision and the recall to work together. It's the overall, detective. So F1 is the balance score. Recall is how many actually, the models that we used in our ML pipeline, how many it found out to be sick, how many people are sick actually. and precision is about when they are sick, how often are they right. Okay, so these are the some of the the validation scores that we are going to encounter in our machine learning pipelines. We have also CV and CV standard. So this actually tells us if the computer gives the same answer when we test it multiple times. Okay, and also we have R square values, where it tells that it has a range from 0 to 1. So 1 means perfect predictions, 0.5 means okay predictions, or negative means really bad predictions. So also you need to consider one thing, that if you have a small data set like this, in this case 100 samples, you won't get R squared in positive values. You will always get negative. So your samples has to be large in number in order to do these machine learning predictions. So yeah, I mean, these are the things that you should consider before diving into the machine learning models. Just understand these scores, and your data has to look perfect. You need to check your data, twice or thrice before you delve into machine learning models. So let's get started. Thank you very much. See you on the other side. So I have some data sets in this folder. Let me open this and I can show you exactly how the data looks like. Okay. So the first header, the first row of the headers is the gene, which you have like gene 1, gene 2, gene 3 and something like that. And the first column is about the samples, your samples, 0, 1, 2, 3, 4, something like that. Okay, so I have like a total of 100 samples starting from 0, and gene starting from 0 to I think 50. And these are some of the values or the target columns that we are going to target in our machine learning model, which is the IC50, and another one is the drug sensitive. Okay, this is one sort of database. Let me show you the other data set, how it looks. So it has also the same samples, same genes, and at last you will see that we have this disease status column, and this disease status is something which determines if the person is healthy or sick. I mean, the samples itself, based on the gene expression data, we can say that whether the this particular sample has some disease or not. So we classify it as 0 and 1. So remember, this is only a test data set for the tutorial purpose. You might have millions of data in your RNA-seq expression analysis. So the thing that you consider should be in this particular format. The CSV file should be in this format, where you have the first row with the headers like gene 1, gene 2, gene 3, something like that, and the first column should be your samples, and the final column should be your target feature. These are the features, like the genes are the features, and the last column is your target column. Okay, so this thing you need to consider first. Okay, and this is the pipeline which is meant for this particular data set, which has the disease status column. Like, we need to classify them. Okay, so this is only for the classification algorithm, and I have written this Python script, and I can upload this onto my Omixium YouTube repository on GitHub, and then you can perform the same with your data sets, and you can also put many different algorithms into it. So what algorithms I have used is random forest, SVC, logistic regression, MLP classifier, yeah, I mean, those are the algorithms that I have used over here. Okay, and some of the metrics like recall, precision, as I discussed before, what should be the validation models that you should be focusing on. So to run that, what you have to do is you have to create an environment. I have already created and installed some of the packages. So source, I'm going to activate this environment, VNB bin activate, and I'm going to show you what are the packages that I have installed. Pip. So to know that what packages have been installed, so you just have to type pip trees requirements.txt, and you can export as requirements.txt. okay, it will write all the packages here, as you can see here. So these are the packages that I have installed. It's matplotlib, numpy, pandas, pillow, plotly, scikit-learn, scipy, cbon, etc., XGBoost, all those algorithms. So this is the requirements.txt file. Okay, and I have created this script where you can call this particular pipeline. So basically what you are doing is from this particular Python file, which is gene expression ml pipeline.py, which is this one, you are importing the class, which is the gene expression ml pipeline. Okay, and then you run your pipeline accordingly. So I'm going to run this, and I'm going to show you how to predict the validation scores, how to analyze the validation scores. And the dataset that I'm using here is the sample gene expression standard, which is this one, which has only one column, that is the disease status. The target column is the disease status. So we are targeting the disease status column over here, and then you split the data, apply PCA. I'll tell you in a bit how to analyze these many functions that I have written over here in this Python file. Okay, so you just have to run this as Python run analysis.py, and basically it will run the whole pipeline. So I'm going to tell you what are the things that I have written over here in this run analysis.py, and how it inspects the data and loads it. So for instance, you can see here we have the okay, let it complete. So it is generating in this particular folder called results, and you see all the results over here. Now it's completed. So first thing what it does is let me open this side by side. Okay, you can see here load and inspect data. This is one function. Okay, so the data sheet shape is 100 and 50. 100 is the samples, 50 is the gene columns or the features. Number of samples 100, number of genes and features is 50. The target distribution, the disease status column is 1 means sick, 0 means healthy. So 50-50 distribution, just for the example purposes. Okay, so the next thing that you are going to do is the pre-processing the data, where you do the log transformation. And the log transformation is really crucial in any sort of RNA expression data. So we are doing this log2 transformation, and we are changing all the values that you see, those float numbers, that we are normalizing it or transforming it into log2 values. Okay, and then we are removing the features with variance 0.01. features after variance filtering is 50, and then we are applying the robust scaling. Next, we are going to split the data. Like we have 100 samples, so 80 samples should be training set and 20 samples should be test sets, which is equivalent to 20% of the data goes for the test size and 80% of the data goes for the training set. Okay, and then we are applying some of the algorithms over here, which is the PCA for the visualization purposes, and then we are training the model for the random forest, SVM, Logistic, Regression, XGBoost, and neural networks. And you can see all those values, as I mentioned previously, the accuracy, the ROC-AUC, and also we are doing some hyperparameter optimization over here using the random forest algorithm and XGBoost, and then we are creating the visualization plots in the results folder. So, and also I have written something here with a function called generate biological interpretation, that you need to understand that which gene plays an important role in your dataset. For me, the gene 3 comes to have importance of around 0.1087, which has the highest importance, and these are the top predictive genes. I mean, this is the ultimate goal, that you need to find out which gene is responsible for the person or the sample to be considered as healthy or disease. Okay, so these are the genes which are responsible. That's the most important thing that you require to analyze on your data set, which is the main goal of the algorithm that we are applying here. And then we have some model performance metrics like CV-ROC, test ROC-AUC, and the test accuracy. You can see that we have some accuracy of 70% here, 90, 80% here, 75% here, and 80% over here. And then you have the classification report with the precision, recall, F1 score, and support. Okay, these are some of the interpretations. So let me also explain you the results from the first data set. So this is what I was explaining previously, and you can see that what the results that we got from our first data set. Logistic regression has 88% ROC-AUC. So from a scale from 0 to 1 or 0 to 100%, 80% of the data has predicted that has well categorized the healthy and the sick person, which is 80%, which is almost a great detective. Okay, excellent. And overall accuracy is 80%, and this is the winner for our model. So likewise, subsequent algorithms have also similar values. And SVM performs really bad, which is 50%, terrible. It's like flipping a coin. You might get head, you might get tail. Okay, you never know. But the overall accuracy is 90%. So yes, the difference. If you get the accuracy, which is like 75%, 80%, 90%, something like that, but you need to check the ROC-AUC values in any of the machine learning models, because this is important. I mean, this is the real detective that is defining your data set and also defining what your data set actually has. Okay, so as you can see here, it has the accuracy of 90%, but ROC-AUC is like 50%, which is terrible. You know, it cannot categorize the healthy versus the sick people or the diseased people. Okay, so why did the SVM fail here even with the 90% accuracy? This is like a detective who always says everyone is healthy. They might be right 90% of the time if the most people are healthy, but they are completely useless at finding the sick people. So that's why the ROC-AUC is really important in any sort of machine learning models. You never go for the overall accuracy. So if you get accuracy like 90%, but your ROC-AUC is like 50% or even less, that means your machine learning algorithm is completely wrong. So be careful with the accuracy versus the ROC-AUC. Okay, so yeah, this is the first data set that I have explained here. I have another script where you can target two variables for the target columns, two columns for the target variables. For instance, in this particular data, like drug resistance, let me show you. So we have these IC50 drug values, IC50 values, and we have the drug sensitivity, which is a classification, and this is a regression value because you have float numbers over here, right? So we are targeting these two columns. So in order to target these two columns with these 50 features, what you have to do is I have written another pipeline where you can apply the same logic but with two different columns. For instance, so I name it as enhanced gene expression pipeline, and you can see here we are targeting classification algorithm to the drug sensitive column, which has a 1 and 0, and then a regression target to IC50 drug X. These are the IC50 values. That means they have some numbers. So always apply regression to the numbers, like the float numbers, and for the classification like a 0 and 1, you apply this classification technique. And rest of the things are same, training the model, splitting it, visualization, and then generating biological interpretation, etc. So I'm going to run this Python run analysis 2.py. I'm going to upload all the scripts, so don't worry about that. So it will create a folder called ML results, something like this, and it will also create all the plots. And by the way, from the first plot or the first script, let me show you, let it complete first, and then I will show you. From the first analysis, this gene expression ml.pipeline, it has created a results folder where you have all the plots in PNG and PDF as well. Okay, so you can see the ROC-AUC scores, ROC curves, confusion matrix. These are the top 20 feature importance genes from the random forest. This is the PCA visualization, how well your data has been categorized. This is the precision recall curves, this is the learning curve, and this is the model performance heat map. Okay, you get a comprehensive plot so that you can actually look into the results in a comprehensive manner. So it gives a top predictive genes table or a CSV file where you have the gene names over here and what is the importance of each and every gene out of your data set. So yeah, let me show you this one, this particular pipeline, which is the second pipeline which we are targeting. These two columns, they are saved into the ML results folder. You see the data set shape and size 151, and you have all the statistics about the data sets, and then it pre-process the data, apply the log2 transformation, okay, and then split the data into 20% test set and 80% training samples, and then it applies the classification models such as Logistic, Regression, Random Forest, XGBoost, and the regression models like Random Forest, XGBoost. Okay, you can apply all the different algorithms that you encounter in recent 2025 algorithms. So this is just an example. You can take the parameters and just apply all the neural network models. You might have seen my previous video regarding the QSAR ML. You can take all those algorithms and apply the same with the RNA sequencing data. You might get very good results out of that. Okay, so in this way you perform this, and you can see the plots over here. So this is the comprehensive analysis plots. As you can see, the ROC-AUC, ROC curves, the PCA, how well your data has been categorized. This is the recall curves, this is the learning curve, this is the model performance heat map, and these are the R-square values. Of course, the R-square values that you see over here is in negative because I have only 100 samples, but if you have millions of data points, then your things will be much more valuable. You get a very nice R-square values. This is the second data set. So imagine that you have drugs that you have given to the healthy people and the sick people, like a placebo control, and you want to find out that will the drug work, yes or no. It's like guessing if the medicine will help someone feel better, and how much drug is needed is basically the IC50. How many spoons that you have given to the patient, that's your IC50 values. Okay, so again, the accuracy, which is 70 to 90% means your data set is good. I mean, your predictions are good. ROC-AUC, as I mentioned, if it is above 65% or 70%, that means, yeah, it does a good job in predicting both the diseased and the healthy people, or in this case, the drug sensitivity, which is 1 and 0 with the IC50 values, okay? And the CV means that if you do it multiple times, then how likely you are getting the scores exactly similar, okay? And what is the standard deviation that you are getting out of that? So it has to be consistent if you perform the same thing multiple times, okay? That's what the CV means. And in this case, our logistic regression has 80% accuracy, and ROC-AUC is like 80%, 88% actually. So, and random forest has 70% accuracy with 83% ROC-AUC. So you never go for the test accuracy, but rather you go for ROC-AUC. Okay, SVM again is the same thing. 90% of the, shows that it has a good accuracy for the ML models, but ROC-AUC is like 50%. Okay, the same thing for your precision recall F1 score. So drugs that doesn't work, which is 0, the precision is 75%, recall is 90, F1 is 82. And what this means is good at finding non-working drugs. And these scores are good at confirming the working drugs. And R square is something related to the accuracy, always correlated with the regression values, because you have the float numbers over there, which is the IC50. How well the data has been correlated, as you can see from the plot as well. So you have these R square values, and you can see that it's completely negative R square. So these are the true IC50 values, and you can see these are the predicted IC50 values. It might fit or it might not fit, because data set is like 100 rows. So if you have millions of data, then it might actually make sense. It will actually make sense, okay, in your case. So these are some of the validation algorithms that you should take into account. And this is the model results summary that you get from your data set. And these are some of the feature importance of the PCA or the principal components that you get from the data sets. You get all the plots over here. Okay. So yeah, this is how you perform machine learning model. And I'm going to upload all the codes to my repository, and you can perform the same with your data set. But the data set has to look like this, or you can modify the Python script as well.